Hello there and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Adjust your pillow, let your body sink into wherever you're resting, and know that there's nowhere else you need to be. Where in the world are you watching from? A quiet bedroom where the day has finally released its hold? A cozy corner where the stars might be visible through your window? Tonight we're going to explore one of the universe's most profound boundaries, absolute zero. The coldest temperature possible, negative 459 degrees Fahrenheit. At this almost unreachable limit, matter transforms in ways that seem impossible. Atoms behave like waves instead of particles. Liquids climb up walls. Electricity flows without resistance forever. We'll discover how scientists spent 3 centuries pursuing this limit, understand why the third law of thermodynamics says we can never quite reach it, and contemplate what these strange quantum behaviours reveal about the fundamental nature of reality itself. But don't worry, this isn't going to be a frantic race through complex physics equations or a breathless countdown to some dramatic revelation. Instead, we'll move slowly and carefully through the story of cold, taking our time with each discovery, each strange phenomenon, each quiet insight. By the end, I think you'll find that absolute zero isn't really about cold at all, but about simplicity, about the universe revealing its most basic truths when everything else falls away. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting these slow journeys through space and time. So settle in, let your shoulders drop away from your ears, take a slow breath in and let it out even slower, and let's begin our slow drift toward absolute zero, toward the coldest possible cold, toward the place where matter stops behaving like anything we recognize and starts revealing secrets that have been hidden in warmth. There's nowhere you need to be right now, nothing you need to solve. Just listen and let the story unfold, gentle and patient as winter starlight. Temperature, when you really think about it, is motion. It's the jiggling of atoms, the vibration of molecules, the kinetic dance that happens at scales far too small to see. When you touch something hot, you're feeling atoms that are moving frantically, careening into each other with tremendous energy. When you touch something cold, those atoms are moving more slowly, more gently, their dance becoming calm and measured. This understanding didn't come easily to us. For most of human history, heat was thought to be a substance, an invisible fluid called caloric that flowed from hot objects to cold ones. The idea made intuitive sense. Pour water from one cup to another and the level equalizes. Perhaps heat worked the same way. But in the late 1700s, a man named Count Rumford noticed something troubling while supervising the boring of cannons. The metal got hot, intensely hot, seemingly without limit as long as the boring continued. If heat were a fluid, the metal should have run out eventually, but it never did. What Rumford had stumbled upon, though he couldn't fully articulate it, was that heat and motion were the same thing. The friction of boring was forcing atoms to move faster, and that motion was what we experience as heat. This insight, refined and expanded by scientists like James Joule in the 1840s, revolutionized our understanding. Temperature wasn't about a substance flowing between objects. It was about energy, about movement, about the fundamental restlessness of matter. And this realization led to a profound question. If temperature is motion, and if you could somehow make atoms stop moving entirely, what would happen? What would matter become when all motion ceased? The answer, scientists gradually realized, was negative 459.67 degrees Fahrenheit. 0 degrees Kelvin. Absolute zero. The coldest possible cold. Not because we lack the technology to go colder, but because there is no colder to go to. It's the bottom of the thermometer, the edge of the map, the point where motion itself surrenders. But here's what makes absolute zero so fascinating. It's not just a very cold temperature, it's a threshold, a boundary, where the normal rules of matter begin to break down and quantum mechanics takes over completely. At room temperature, quantum effects are there, subtle and hidden beneath the chaos of atomic motion. But at absolute zero, with motion stripped away, quantum behaviour becomes the only behaviour. Matter doesn't just get cold, it gets strange. And this strangeness has taught us more about the universe than perhaps any other realm of physics. Which brings us naturally to the question of what, exactly, makes matter behave so differently when we push it toward this ultimate limit. To understand that, we need to look at what happens to atoms as they slow down. Imagine an atom at room temperature. It's moving, always moving, vibrating in place if it's locked in a solid, or careening through space if it's part of a gas. The speed is extraordinary. A single nitrogen molecule in the air around you right now is travelling at roughly 1,000 miles per hour, bouncing off other molecules, changing direction, never still. This motion, this restless energy, is what temperature measures. Now imagine we start cooling things down. We remove energy from the system, bit by bit, and the atoms respond by slowing their dance. At 0 degrees Celsius, water freezes, its molecules locking into crystalline patterns, but they're still vibrating in place, still moving. At negative 78 degrees Celsius, carbon dioxide becomes dry ice, and its molecules are moving more slowly still but moving nonetheless. The colder we go, the calmer the motion becomes. But here's the remarkable thing. According to classical physics, the physics that Newton and Galileo developed, there should be no limit to how slow atoms can move. You could, in theory, extract every last bit of energy and bring them to perfect stillness. Absolute zero would be absolute rest, a state where atoms simply stopped moving entirely, frozen in space like statues. Quantum mechanics says otherwise. In the early 1900s, as physicists began to understand the strange behaviour of matter at atomic scales, they discovered something unsettling. Atoms, it turns out, can never be completely at rest. Even at absolute zero, even with every bit of thermal energy removed, atoms retain what's called zero-point energy, a minimum amount of motion that can never be eliminated. It's not much, this residual motion, but it's enough to ensure that absolute stillness is impossible. Why? The answer lies in Heisenberg's uncertainty principle, one of the foundational insights of quantum mechanics. The principle states that you cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you know where something is, the less precisely you can know how fast it's moving, and vice versa. If an atom were perfectly still at a perfectly known position, you would know both its position and its momentum with infinite precision, which the uncertainty principle forbids. So atoms at absolute zero are not still. They're in their ground state, their lowest possible energy state, but they're still quivering with zero-point energy, still obeying the uncertainty principle's demands. This residual motion is small, far smaller than thermal motion at any reasonable temperature, but it's there, permanent and ineradicable. It's the universe's way of saying that perfect stillness, like perfection itself, is an ideal that can never quite be reached. And this is where matter starts to get strange. Because when you cool atoms down to the point where thermal motion becomes negligible and zero-point energy dominates, quantum effects that are usually invisible suddenly become prominent. Atoms stop behaving like tiny billiard balls bouncing around randomly. They start behaving like waves, like probability clouds, like entities that can exist in multiple states simultaneously until you look at them. The story of how we discovered this strangeness begins not with abstract theory, but with a substance we use every day to inflate balloons. A substance that, when cooled to just a few degrees above absolute zero, does something so bizarre that the scientists who first saw it thought their equipment must be broken. Helium is strange even before you cool it down. It's the only element that remains liquid at atmospheric pressure all the way down to absolute zero. Hydrogen freezes at negative 259 degrees Celsius. Nitrogen becomes solid at negative 210. But helium, stubborn and unusual, refuses to solidify no matter how cold you make it unless you also apply tremendous pressure. The reason has to do with how light helium atoms are and how weakly they attract each other. Their zero-point energy is enough to keep them from settling into a solid structure. But the real strangeness begins at negative 271 degrees Celsius, just over 2 degrees above absolute zero. At this temperature, liquid helium undergoes a phase transition unlike anything else in nature. It becomes what physicists call helium-2, or more evocatively, a superfluid. And superfluids don't obey the normal rules of liquids. The first person to observe this transition was a Dutch physicist named Heike Kamerlingh-Onnes in 1911. Onnes had spent years perfecting the technology to liquefy helium, which requires reaching temperatures colder than anything else in nature. When he finally succeeded and began cooling liquid helium further, he noticed something peculiar. The liquid's viscosity, its resistance to flow, dropped suddenly and dramatically. Below the transition temperature, helium seemed to flow without any friction whatsoever. But the full strangeness of superfluid helium wasn't understood until the 1930s and 40s, when physicists like Piotr Kapitsa in the Soviet Union and John Allen and Don Misner in Britain conducted a series of experiments that revealed just how bizarre this state of matter truly was. Superfluid helium could flow through impossibly tiny cracks that would stop any normal liquid. It had effectively zero viscosity, meaning once you got it flowing, it would continue flowing forever without slowing down. Pour it into a container, and it would form a thin film that would creep up the walls, over the rim, and down the outside, emptying the container from the inside out. This behaviour defied everything physicists knew about liquids. Viscosity, the internal friction that makes honey flow slowly and water flow quickly, was thought to be a fundamental property of all fluids. Yet here was a fluid with no viscosity at all. It was as if the helium atoms had stopped acting as individuals and had merged into a single quantum entity, moving together in perfect coordination. And that's essentially what was happening. At the superfluid transition, a significant fraction of the helium atoms condense into the same quantum ground state. They stop being discrete particles and become part of a single macroscopic quantum wave function. In normal matter, quantum effects are confined to the microscopic realm, affecting individual atoms or small groups. But in superfluid helium, quantum behaviour scales up to involve trillions upon trillions of atoms acting as one. You can literally see quantum mechanics with your naked eye, watching helium film creep up container walls in seeming defiance of gravity. The theoretical explanation for this came from Fritz London in 1938, building on ideas about quantum statistics developed by Satyendra Bose and Albert Einstein. Helium-4 atoms are bosons, a class of particles that can occupy the same quantum state. When cooled sufficiently, many helium atoms drop into the ground state simultaneously, forming what's called a Bose-Einstein condensate, though that term wasn't used until later. This condensate behaves as a single quantum object, and its properties are governed by quantum mechanics rather than classical fluid dynamics. Superfluid helium opened a door. It was the first macroscopic quantum phenomenon ever observed, the first proof that quantum strangeness wasn't confined to the atomic realm, but could scale up to quantities you could hold in your hand. And it hinted at something even more profound, that absolute zero isn't just cold, but a threshold where entirely new states of matter become possible. States that exist nowhere else in the universe except in the coldest laboratories on Earth, and perhaps in the cores of dead stars. Which leads us to consider what, exactly, this superfluid helium can do that seems so impossible to our everyday experience. The most visually striking property of superfluid helium is its tendency to climb. Place superfluid helium in a container, and within seconds, a thin film begins creeping up the inner walls. It moves slowly but inexorably, climbing higher and higher until it reaches the rim. Then it flows over the edge and down the outside, dripping back into any vessel below. If the container has no vessel beneath it, the helium will empty itself entirely, flowing up, over and away until nothing remains. This behaviour is called the Rollin film, named after Bernard Rollin, who first observed it in 1936 while working in the Oxford laboratory of physicist Frederick Lindemann. Rollin was studying liquid helium at temperatures just above the superfluid transition when he noticed something peculiar. The helium level in his container was dropping, even though the system was sealed. At first, he thought there must be a leak, but when he carefully examined the apparatus, he saw what was happening. A nearly invisible film of helium, perhaps 30 atoms thick, was creeping up the walls, over the rim, and dripping away. The film moves because of a peculiar property of superfluids. They have no surface tension in the traditional sense, and they wet everything perfectly. In a normal liquid, surface tension creates a balance between the liquid's cohesion and its adhesion to container walls. Water, for instance, curves upward slightly where it meets glass, forming a meniscus. But superfluid helium doesn't form a meniscus. Instead, it spreads out completely, forming the thinnest possible film that still allows quantum mechanical interaction with the surface. And because the superfluid has zero viscosity, this film flows freely, driven by whatever forces act upon it. The slightest temperature gradient, the tiniest gravitational pull, and the film begins to move. Once moving, it continues indefinitely unless some force stops it. In practice, this means that containing superfluid helium is extraordinarily difficult. Any imperfection in the container, any microscopic crack or crevice, and the helium will find it and flow through it. But the strangeness goes deeper than just climbing walls. Superfluid helium also exhibits what physicists call fountain effects. If you take two containers of superfluid helium connected by a narrow tube plugged with a porous material, and you heat one container, helium flows from the cold container toward the warm one. This seems backwards. Heat normally drives fluids away, causing expansion and convection. But in superfluid helium, the normal component of the fluid, the part that still retains some thermal energy, cannot easily flow through the porous plug. The superfluid component, however, flows freely. The result is that the superfluid flows toward the heat, trying to equalize the ratio of normal to superfluid throughout the system. If you create enough of a temperature difference, the pressure in the heated container can build up so much that helium shoots upward in a fountain several centimeters high. Experiments with superfluid helium sometimes feel more like magic shows than physics. Researchers have created persistent currents in superfluid helium that flow in loops for years without slowing down. They've watched vortices form in spinning superfluid tiny tornadoes of quantum behaviour that never dissipate. They've observed second sound, a kind of wave that travels through superfluid helium carrying temperature variations rather than pressure variations, something that has no analogue in normal fluids. All of these phenomena arise from the same basic fact. In superfluid helium, a macroscopic number of atoms have lost their individual identities and merged into a single quantum state. The superfluid isn't a collection of trillions of atoms moving independently. It's one quantum object, vast and strange, obeying rules that seem impossible when you first encounter them. And helium wasn't the only substance that revealed quantum strangeness at ultra-low temperatures. While physicists were unravelling the mysteries of superfluidity, others were discovering that electricity itself behaves in impossible ways when matter gets cold enough. Which brings us to the story of how scientists spent 3 centuries trying to reach absolute zero, and what they found along the way. The pursuit of cold is one of the longest-running quests in the history of science. Long before anyone understood what temperature really was, people knew that cold could preserve food, relieve pain, and reveal hidden properties of matter. Ancient Romans stored snow in insulated pits to cool their wine in summer. Medieval Islamic scholars experimented with evaporative cooling. But it wasn't until the scientific revolution that the race toward absolute zero truly began. The first major breakthrough came in the 1650s, when Robert Boyle and others began studying the behaviour of gases. Boyle discovered that the volume of a gas is inversely proportional to its pressure, a relationship that hinted at deeper connections between temperature, pressure, and the nature of matter. In the 1770s, Antoine Lavoisier and others began to understand heat as a measurable quantity, something that could be added or removed systematically. But the real race started in the early 1800s, when scientists began achieving temperatures far below anything found in nature. The key was understanding phase transitions, the process by which substances change from gas to liquid to solid. When a gas becomes liquid, it releases energy, cooling itself in the process. By carefully controlling pressure and allowing gases to evaporate, scientists could achieve progressively lower temperatures. In 1845, Michael Faraday liquefied several gases, including ammonia and carbon dioxide, reaching temperatures around -78 degrees Celsius. This was colder than anything humans had previously achieved, but the real prizes, the permanent gases as they were called, hydrogen, oxygen, and nitrogen, remained stubbornly gaseous. Many scientists suspected these gases could never be liquefied, that they would remain gaseous no matter how much pressure you applied or how cold you made them. This suspicion was disproven in 1877, when Louis Cailletet in France and Raoul Pictet in Switzerland independently liquefied oxygen, reaching temperatures around -183 degrees Celsius. Nitrogen followed soon after, and in 1898, James Dewar succeeded in liquefying hydrogen, achieving -252 degrees Celsius. Each breakthrough required extraordinary experimental skill. The gases had to be compressed to tremendous pressures and then allowed to expand suddenly, which cooled them through what's called the Joule-Thomson effect. The cooled gas would then liquefy, at least briefly, before warming back up. Dewar's achievement left only one permanent gas unliquefied: helium. This rare element, first discovered in the sun's spectrum in 1868, was extraordinarily difficult to work with. It required temperatures lower than anything achieved before, and it required starting with pure helium gas, which was itself difficult to obtain. The race to liquefy helium became a matter of national pride, with laboratories in Britain, the Netherlands, and elsewhere competing to be first. The winner was Heike Kamerlingh-Onnes, working at Leiden University in the Netherlands. In 1908, after years of methodical preparation, Onnes and his team successfully liquefied helium, reaching -269 degrees Celsius, just 4 degrees above absolute zero. The achievement opened up an entirely new realm of experimental physics. For the first time, scientists could study matter at temperatures where quantum effects dominated. Onnes immediately began exploring this new realm. In 1911, he discovered that mercury, when cooled to near absolute zero, suddenly lost all electrical resistance, becoming what he called a superconductor. This discovery would prove as revolutionary as superfluidity, revealing yet another way that matter behaves impossibly at ultra-low temperatures. But before we explore superconductivity, it's worth pausing to appreciate what these early pioneers accomplished. The journey from room temperature to liquid helium required dropping the temperature by roughly 300 degrees Celsius. Each step required new techniques, new materials, new understanding. And each step revealed something unexpected about matter, about energy, about the universe's fundamental structure. The race to zero wasn't just about reaching cold temperatures. It was about pushing into unknown territory and discovering that the universe is stranger, more subtle, more quantum than anyone had imagined. And that strangeness, as we'll see, was only beginning to reveal itself. When Heike Kamerlingh-Onnes discovered superconductivity in 1911, he had no idea what he was seeing. He was measuring the electrical resistance of mercury as it cooled toward absolute zero, expecting the resistance to decrease gradually as the atom's thermal motion subsided. Instead, at 4.2 degrees Kelvin, the resistance vanished completely, not mostly, not approximately, completely. The mercury had become a perfect conductor, a material through which electricity could flow without any loss whatsoever. Ons repeated the experiment over and over, refining his technique, eliminating possible sources of error. The result never changed. Below a certain critical temperature, mercury's resistance dropped to 0. He tried other metals and found that several, including lead and tin, exhibited the same behaviour. A new state of matter had been discovered, as fundamental and strange as superfluidity, governed by quantum mechanics but visible at macroscopic scales. But understanding why materials became superconducting would take another 46 years. The explanation, when it finally came in 1957, involved one of the most counterintuitive ideas in physics, that electrons, which normally repel each other because they all carry negative charge, could under certain conditions attract each other and form pairs. The theory was developed by John Bardeen, Leon Cooper, and John Robert Schrieffer, and it's known as BCS theory after their initials. The key insight was that in certain materials at low temperatures, electrons can interact indirectly through the crystal lattice, the regular arrangement of atoms that makes up a solid. Here's how it works. An electron moving through a metal attracts nearby positive ions in the lattice, pulling them slightly out of position. This creates a region of slightly enhanced positive charge, which in turn attracts a second electron. The two electrons become correlated, paired through their mutual interaction with the lattice. These pairs, called Cooper pairs, behave differently from individual electrons. Electrons are fermions, particles that obey the Pauli exclusion principle, which forbids two identical fermions from occupying the same quantum state. But Cooper pairs, being pairs, behave as bosons, particles that can occupy the same state. And just as helium atoms condense into a single quantum state to form a superfluid, Cooper pairs condense into a single quantum state that extends throughout the entire superconductor. This macroscopic quantum state is what gives superconductors their remarkable properties. The paired electrons move together, coordinated like dancers in a perfectly choreographed ballet. If you try to scatter one electron, to deflect it off an impurity or lattice vibration, you have to scatter its partner too. This dramatically reduces the probability of scattering, effectively eliminating electrical resistance. The pairing energy is small, typically corresponding to temperatures of just a few degrees Kelvin. Above the critical temperature, thermal energy is enough to break the pairs apart, and the material reverts to normal conductivity. But below the critical temperature, the pairs are stable, and the superconducting state emerges. What makes this so remarkable is that superconductivity, like superfluidity, is a purely quantum phenomenon scaled up to macroscopic sizes. In a superconducting wire, billions upon billions of electron pairs move in perfect unison. Their quantum states lock together by the constraints of quantum mechanics. You can measure this with simple electrical instruments. You can see the effects with your naked eye. Quantum mechanics, usually confined to atomic scales, becomes tangible and manipulable. The discovery of BCS theory earned Bardeen, Cooper and Schrieffer the Nobel Prize in 1972. It was one of the crowning achievements of 20th century physics, explaining a phenomenon that had puzzled scientists for nearly half a century. But it also raised new questions, particularly about what other states of matter might exist at absolute zero, waiting to be discovered. And one of the most dramatic effects of superconductivity, as scientists quickly learned, is how these materials interact with magnetic fields. A perfect conductor, if such a thing could exist, would carry electrical current without any energy loss. Electricity flowing through a loop of perfect conductor would, in principle, continue flowing forever, never slowing down, never dissipating as heat. This seems impossible. A violation of everyday experience where friction and resistance gradually bring everything to rest. Yet superconductors are exactly this impossible thing. The implications are extraordinary. If you establish a current in a superconducting loop and then disconnect the power source, the current continues flowing. Not for minutes, not for hours. In principle, forever. The electrons, bound into Cooper pairs and condensed into a macroscopic quantum state, have nowhere to lose energy. There's no resistance to dissipate the current as heat. The only limit is the stability of the superconducting state itself. This has been demonstrated directly. Scientists have created persistent currents in superconducting loops and measured them over periods of years. The current shows no detectable decrease. Extrapolating from these measurements, physicists estimate that a persistent current in a superconducting loop could continue flowing for billions of years, far longer than the current age of the universe. This property has practical applications. Superconducting magnets, which are simply coils of superconducting wire carrying large currents, can produce incredibly strong magnetic fields without any energy input beyond what's needed to maintain the low temperature. Once the current is established, it flows continuously, maintaining the magnetic field indefinitely. These magnets are used in MRI machines in hospitals, in particle accelerators like the Large Hadron Collider, and in experimental fusion reactors where extreme magnetic fields are needed to contain superhot plasma. But there's another property of superconductors, discovered just as early as zero resistance, that's even more counterintuitive. In 1933, Walter Meissner and Robert Oxenfeld discovered that superconductors don't just conduct electricity perfectly, they also expel magnetic fields from their interior. If you take a superconducting material and cool it below its critical temperature in the presence of a magnetic field, the field is pushed out completely. The interior of the superconductor becomes a magnetic void. This effect, now called the Meissner effect, seems strange at first. After all, normal conductors allow magnetic fields to penetrate them easily, but superconductors are different. The macroscopic quantum state that makes superconductivity possible also constrains how magnetic fields can behave. The superconducting electrons respond to any attempt by a magnetic field to penetrate by setting up currents on the surface that exactly cancel the field inside. These screening currents flow without resistance, maintaining themselves indefinitely and keeping the interior field free. The Meissner effect has a dramatic visible consequence: magnetic levitation. If you place a small magnet above a superconductor, the superconductor's perfect diamagnetism, its expulsion of magnetic fields, creates a repulsive force that can levitate the magnet in mid-air. The magnet floats, suspended by quantum mechanics. Hovering over the superconductor as if held by invisible hands, early demonstrations of magnetic levitation over superconductors became iconic images of quantum physics. A small disk floating motionless above a chunk of material cooled with liquid nitrogen, defying gravity through nothing but quantum mechanical principles. It seemed like magic, like science fiction made real. And in a sense, it was. The levitation wasn't held up by any mechanical force, any chemical reaction, any classical physics principle. It was held up by the quantum nature of superconductivity itself. This perfect expulsion of magnetic fields, combined with zero electrical resistance, makes superconductors unique among materials. They're not just good conductors. They're a fundamentally different state of matter, one where quantum coherence extends across macroscopic distances and produces effects that have no classical analogue. And as scientists explored superconductors more deeply, they discovered that the story was even richer than they'd imagined. Some superconductors could trap magnetic field lines in tiny tubes, creating quantized vortices. Others could transition between superconducting and normal states in complex patterns. The physics of superconductivity opened up an entire subdiscipline, rich with phenomena that continue to surprise and puzzle physicists today. Which raises a deeper question. If electrons can form these coordinated pairs that move without resistance, what else might be possible at temperatures approaching absolute zero? Picture a small rare earth magnet, the kind you might use to hold papers on a refrigerator, hovering motionless above a chunk of dark ceramic material. There are no strings, no hidden supports, no clever tricks. the magnet simply floats, stable and serene. Suspended by invisible quantum forces, this is magnetic levitation through the Meissner effect, and it's one of the most visually striking demonstrations of quantum mechanics at work. The stability of this levitation is remarkable. Push the magnet gently, and it oscillates back to its equilibrium position. Try to flip it over, and the repulsive force adjusts to maintain the levitation. The magnet is locked in place by the superconductor's perfect diamagnetism, held at a precise distance where the repulsive force exactly balances the magnet's weight. This phenomenon has fascinated both physicists and the public since its discovery. Early demonstrations often used low-temperature superconductors that required cooling with liquid helium, making them expensive and difficult to maintain. But in 1986, a breakthrough changed everything. Scientists discovered a new class of materials called high-temperature superconductors that became superconducting at temperatures as high as 93 degrees Kelvin, warm enough to be cooled with relatively inexpensive liquid nitrogen. These high-temperature superconductors, despite their name, are still extremely cold by everyday standards. 93 degrees Kelvin is negative 180 degrees Celsius, far colder than any naturally occurring temperature on Earth, except perhaps in the upper atmosphere. But compared to liquid helium temperatures, which require 4 degrees Kelvin, they were remarkably accessible. Suddenly, demonstrations of magnetic levitation became practical for classrooms and science museums around the world. High-temperature superconductors also introduced new complexities. Unlike conventional superconductors explained by BCS theory, these materials, mostly copper oxide ceramics with complex crystal structures, superconduct through mechanisms that physicists still don't fully understand. The pairing mechanism seems different, possibly involving quantum fluctuations of the lattice itself or interactions between electrons through different channels. Decades after their discovery, high-temperature superconductivity remains one of the great unsolved problems in condensed matter physics. But regardless of the mechanism, the effects are similar. Cool these materials below their critical temperature, and they expel magnetic fields, exhibit zero resistance, and can levitate magnets through the Meissner effect. Some high-temperature superconductors can even trap magnetic field lines in quantized vortices, allowing for stable levitation even when the magnet is placed directly on the superconductor. This flux pinning, as it's called, creates a more robust kind of levitation, where the magnet can be rotated, tilted, or even inverted, yet remains stably suspended. The dream, of course, has been to create room-temperature superconductors, materials that exhibit superconductivity at ordinary temperatures without any cooling whatsoever. Such materials would revolutionize electrical transmission, eliminating energy losses in power lines. They would enable ultra-efficient motors and generators. They would make magnetic levitation practical for high-speed trains and other transportation applications. Despite decades of research, room-temperature superconductivity at ambient pressure remains elusive. Claims of room-temperature superconductivity in exotic materials under extreme pressure have been made, but these materials remain impractical for real-world applications. The highest critical temperature for a superconductor at ordinary pressures is still well below the freezing point of water. Yet the search continues, driven by both scientific curiosity and practical ambition. Every new class of superconducting materials reveals something unexpected about how electrons can cooperate at low temperatures. Each discovery hints that there might be other mechanisms, other ways to achieve superconductivity, waiting to be found. And magnetic levitation, that dramatic floating magnet, remains one of the most powerful symbols of what quantum mechanics can do when given full rein. It's matter behaving impossibly, held in the air by nothing but the quantum coordination of trillions of electrons, all moving together in ways that classical physics says should be impossible. As we contemplate these suspended magnets, these currents that flow forever, we're seeing quantum mechanics not as an abstract mathematical formalism, but as a tangible force that shapes the behavior of matter in the real world. One of the deepest mysteries in quantum mechanics is wave-particle duality, the idea that matter and energy can behave as both particles and waves depending on how you observe them. An electron, for instance, sometimes acts like a tiny ball of matter, localized in space, bouncing off things like a miniature billiard ball. Other times, it acts like a wave, spreading out in space, interfering with itself, exhibiting behavior that only waves can show. This duality troubled physicists from the beginning of quantum mechanics. It seemed contradictory, even paradoxical. How could something be both a particle and a wave? The answer, as it turned out, is that these categories are too limited. Quantum objects are neither particles nor waves in the classical sense. They're something else entirely, quantum entities that exhibit particle-like or wave-like behavior depending on the experimental context. But at high temperatures, the wave nature of matter is difficult to observe. The de Broglie wavelength, the characteristic wavelength associated with a particle's motion, is inversely proportional to its momentum. Fast-moving particles at high temperatures have very short wavelengths, too short to produce noticeable interference effects. They behave, for all practical purposes, like classical particles. Cool things down, though, and the situation changes dramatically. As particles slow down, their de Broglie wavelengths increase. Eventually, at temperatures approaching absolute zero, the wavelengths become comparable to the spacing between particles. The wave functions of adjacent particles begin to overlap, and suddenly you can no longer treat them as separate, localized entities. They start acting like a single, extended wave. This is part of what happens in both superfluids and superconductors. The particles, whether helium atoms in superfluid helium or electron pairs in a superconductor, condense into states where their wave functions overlap significantly. They lose their individual identities and become part of a macroscopic quantum wave that extends throughout the material. But the wave nature of matter at low temperatures goes deeper than just overlapping wave functions. In 1924, a young French physicist named Louis de Broglie proposed that all matter, not just light, has wave properties. His idea was revolutionary and initially met with skepticism. But within a few years, experiments by Clinton Davison and Lester Germer, and independently by George Paget Thompson, demonstrated that electrons could be diffracted by crystals just like X-rays, proving that matter really does have wave-like properties. This wave nature becomes increasingly important as temperatures drop. In atom interferometry, a technique developed in the 1990s, researchers use lasers to split the wave function of an atom into two paths and then recombine them, creating interference patterns that reveal subtle forces and accelerations. These interferometers only work because at the low speeds involved, the atom's de Broglie wavelengths are large enough to observe clear interference. The same principles apply in studying ultra-cold gases. When atoms are cooled to microkelvin temperatures, millionths of a degree above absolute zero, their wave functions extend over distances comparable to the spacing between atoms. The gas becomes quantum degenerate, meaning the atom's quantum statistics, whether they're bosons or fermions, start to matter. Bosons can condense into the same quantum state, forming Bose-Einstein condensates. Fermions, forbidden by the Pauli exclusion principle from occupying the same state, form a degenerate Fermi gas where all the lowest energy states are filled. In both cases, the gas no longer behaves like a collection of classical particles. It behaves like a quantum fluid, with properties governed by wave mechanics rather than particle mechanics. You can create waves in these ultra-cold gases, excitations that propagate like ripples on a pond. You can observe quantum vortices, whirlpools of quantized circulation. You can even create matter wave lasers, called atom lasers, where atoms are emitted in a coherent beam just like photons in a light laser. All of this behavior emerges because at low temperatures the wave nature of matter dominates. Particles stop being particles in the classical sense. They become delocalized, spread out in space. Interfering with themselves and with each other, the universe at absolute zero is fundamentally wavy, fundamentally quantum, fundamentally strange. And this wave nature isn't just an abstract theoretical construct, it has practical consequences that researchers are only beginning to explore. Quantum sensors based on atom interferometry can detect gravitational waves, measure fundamental constants, and navigate with extraordinary precision. Quantum computers, which rely on maintaining quantum coherence in systems of qubits, work better at low temperatures where thermal noise is minimized and quantum effects dominate. The question, wave or particle, turns out to have been the wrong question all along. Matter is quantum, and quantum means both and neither, depending on what you're looking at and how you're looking at it. And nowhere is this quantum nature more apparent than at the lowest temperatures, where the universe strips away the classical facade and reveals the wave mechanics beneath. In 1927, Werner Heisenberg published a paper that would change physics forever. The paper introduced what became known as the uncertainty principle, a fundamental limit on how precisely you can know certain pairs of properties simultaneously. The most famous version concerns position and momentum. The more precisely you know where something is, the less precisely you can know how fast it's moving, and vice versa. But the principle applies to other pairs of properties too, including energy and time. Heisenberg's uncertainty principle isn't about measurement limitations or experimental error. It's not that we could know both position and momentum precisely if only we had better instruments. The uncertainty is fundamental, built into the nature of reality at the quantum level. It arises from the wave nature of matter. A wave that's perfectly localized in space, a precise position, requires a mixture of many different wavelengths, which means many different momenta. A wave with a perfectly defined wavelength, a precise momentum, is spread out over all space with no definite position. This principle has profound implications for absolute zero. If particles could truly reach perfect rest, they would have zero momentum, perfectly known. By the uncertainty principle, their position would become completely uncertain, infinite in extent. The universe forbids this. Even at absolute zero, particles must retain some minimum motion, some zero-point energy, to satisfy the demands of quantum mechanics. This zero-point energy is everywhere. The atoms in the chair you're sitting on, even if cooled to absolute zero, would still be vibrating in place. The electrons orbiting atomic nuclei, even in their ground states, retain kinetic energy. Even the vacuum of space, supposedly empty, seethes with zero-point fluctuations of quantum fields, virtual particles popping in and out of existence too quickly to be directly observed. The consequences of zero-point energy are subtle but measurable. One of the most famous is the Casimir effect, predicted by Hendrik Casimir in 1948. If you place two uncharged metal plates very close together in a vacuum, they experience an attractive force. The force arises because the quantum vacuum between the plates has slightly less zero-point energy than the vacuum outside. The difference in quantum fluctuations creates a measurable pressure pushing the plates together. The effect was first measured definitively in the 1990s, confirming that zero-point energy is real and has physical consequences. At low temperatures, the uncertainty principle also constrains how precisely you can measure time and energy. The longer you observe a system, the more precisely you can determine its energy. But quick measurements have inherent energy uncertainty. This manifests in phenomena like quantum tunneling, where particles can temporarily borrow energy from the vacuum to overcome barriers they classically couldn't cross, as long as they repay the energy quickly enough that the uncertainty principle isn't violated. In ultra-cold atomic gases, researchers use the uncertainty principle to their advantage. By trapping atoms in optical lattices, grids of light created by intersecting laser beams, they can control the balance between kinetic energy and potential energy precisely. The lattice constrains the atoms' positions, which by the uncertainty principle increases their momentum uncertainty. This interplay between position and momentum, controlled through laser intensity and geometry, allows researchers to simulate condensed matter systems study quantum phase transitions, and explore regimes of physics that would be impossible to access any other way. The uncertainty principle also sets limits on how cold we can make things. To cool atoms, we need to measure their momentum and remove energy selectively. But measuring momentum disturbs position, and the disturbance adds energy back into the system. There's a fundamental limit, set by the uncertainty principle, on how cold we can make a gas using conventional laser cooling techniques. To go colder requires different methods, like evaporative cooling, where the hottest atoms are removed from the system, leaving the coldest behind to thermalize at an even lower temperature. Heisenberg's insight that uncertainty is fundamental rather than incidental revolutionized our understanding of measurement and reality. At high temperatures, where classical physics dominates, we can usually ignore quantum uncertainty. But at absolute zero, where quantum effects become paramount, the uncertainty principle shapes everything. It prevents perfect stillness. It ensures perpetual motion at the smallest scales. It makes the vacuum not empty but alive with quantum fluctuations. And this quantum uncertainty, this fundamental restlessness built into nature, is part of what makes absolute zero so fascinating. It's not a state of perfect rest, but a state of minimal motion, where the universe's quantum nature is laid bare, unobscured by thermal noise. As we move deeper into the quantum realm of ultra-cold matter, we'll encounter phenomena that push the boundaries of what seems possible even further. Entire clouds of atoms acting as single quantum objects. Light brought to a standstill. States of matter that exist nowhere in nature except in our coldest laboratories. The journey towards zero reveals not emptiness but richness, not stillness but profound quantum activity. In 1924, Albert Einstein received a paper from an Indian physicist named Satyendra Nath Bose. Bose had been working on the quantum theory of light, trying to derive Planck's radiation law from first principles. His approach was radical. Instead of treating photons as distinguishable particles, he treated them as indistinguishable, assuming you couldn't tell one photon from another even in principle. Einstein immediately recognized the importance of Bose's work. Not only did it provide an elegant derivation of Planck's law, but the statistical method Bose had developed could be applied to matter particles too. Einstein extended Bose's ideas to atoms and predicted something remarkable. If you cooled a gas of identical bosons, particles like helium-4 atoms that have integer spin, to a sufficiently low temperature, a macroscopic fraction of them would condense into the single lowest energy quantum state. This wasn't ordinary condensation like water vapor becoming liquid. This was quantum condensation, where particles lose their individual identities and merge into a single quantum entity, described by one macroscopic wave function. Einstein predicted that this Bose-Einstein condensation would occur at a characteristic temperature that depends on the particle mass and density. For ordinary gases at normal densities, this temperature was far below anything achievable at the time. For 70 years, Bose-Einstein condensation remained a theoretical curiosity. Physicists knew it must exist. Superfluid helium provided indirect evidence of bosonic condensation, but creating a pure Bose-Einstein condensate in a gas, where the phenomenon could be studied directly, seemed impossibly difficult. The problem was that cooling atoms to the required temperatures, typically microkelvin or below, caused them to stick together and form ordinary liquid or solid phases before reaching the quantum degenerate regime. The breakthrough came in 1995 when two groups of physicists, Eric Cornell and Carl Wieman at the University of Colorado and Wolfgang Kettel at MIT, succeeded in creating Bose-Einstein condensates in dilute gases of rubidium and sodium atoms. They used a combination of laser cooling and evaporative cooling to reach temperatures around 100 nanokelvin, billionths of a degree above absolute zero. At these temperatures, in these rarefied gases, Bose-Einstein condensation occurred before the atoms could stick together and solidify. The result was extraordinary. a cloud of roughly 100,000 atoms, all occupying the same quantum ground state, all described by a single macroscopic wave function. The condensate behaved like a single quantum object, enormous by atomic standards. When photographed using absorption imaging, where a laser beam passes through the gas and casts a shadow of the atomic density, the condensate appeared as a distinct peak in the centre of the cloud, surrounded by a halo of non-condensed atoms. The properties of Bose-Einstein condensates validated everything Einstein and Bose had predicted. The condensates exhibited superfluidity, flowing without viscosity. They supported quantized vortices, tiny tornadoes of circulation that could only rotate at discrete quantized rates. They could be manipulated with lasers, trapped in optical potentials, split into multiple pieces and recombined to create matter wave interference patterns. One of the most striking demonstrations involved creating interference between two separate condensates. Researchers produced two clouds of atoms in their ground state separated in space and then allowed them to expand and overlap. Where the two matter waves met, they interfered, creating a pattern of bright and dark fringes just like the interference pattern you get when two light waves overlap. But these weren't light waves. They were waves of atomic matter, probability distributions for finding atoms, interfering because the atoms in each condensate had lost their individual identities and become parts of coherent quantum waves. Bose-Einstein condensation represents perhaps the clearest example of quantum mechanics scaling up to visible sizes. You can literally see quantum coherence with appropriate imaging equipment. You can watch matter wave packets evolve, split, and interfere. You can create exotic states where atoms are entangled, where measuring one atom instantly affects others regardless of distance. The discovery earned Cornell, Wieman and Kettle the Nobel Prize in 2001, just 6 years after their initial achievement. But the real prize was opening up an entirely new field of research. Bose-Einstein condensates became laboratories for exploring quantum mechanics, testing theories of superfluidity, simulating condensed matter physics, and developing quantum technologies. And as researchers explored these condensates more deeply, they discovered that the quantum world at ultra-low temperatures contained even more surprises, more states of matter, more phenomena that challenged our understanding of what matter could be and do. Imagine a symphony orchestra where every musician plays their own interpretation of the score, slightly out of sync with everyone else. The result is cacophony. Noise, a muddle of individual sounds that don't coherently combine. Now imagine the same orchestra perfectly synchronized, every note timed to perfection, every musician following the same conductor. The result is music, coherent and powerful, far greater than the sum of its parts. Bose-Einstein condensates are like that second orchestra. They're collections of atoms that have synchronized their quantum states so perfectly that they act as one entity. In technical terms, the atoms have all condensed into the same quantum ground state, the lowest energy configuration available. Their individual wave functions overlap completely, merging into a single macroscopic wave function that describes the entire condensate. This coherence has profound consequences. In a normal gas, even a very cold one, each atom is described by its own wave function. The atoms might be in similar states, but they're not in the same state. They maintain separate identities. You could, in principle, label them and track them individually. But in a Bose-Einstein condensate, this individual identity is lost. The atoms are fundamentally indistinguishable, not because we lack the instruments to tell them apart, but because quantum mechanics says they've merged into a single entity. One way to visualize this is through phase coherence. Every quantum wave has a phase, a property that determines where the wave's peaks and troughs are located. When two waves with the same phase overlap, they interfere constructively, adding together to create a larger amplitude. When they're out of phase, they interfere destructively, cancelling out. In a Bose-Einstein condensate, all the atomic wave functions have locked into the same phase throughout the condensate. This phase coherence extends over the entire cloud, sometimes spanning distances of millimeters or more, enormous by atomic standards. This coherence enables phenomena that would be impossible in normal matter. Researchers have created solitons in Bose-Einstein condensates, localized wave packets that maintain their shape as they propagate, neither spreading out nor dissipating. They've observed quantum vortices, regions where the condensate's phase winds around a point, creating quantized circulation. They've even created matter wave lasers, where atoms are extracted from a condensate in a coherent beam, analogous to photons being emitted from an optical laser. The quantum synchrony in condensates also makes them incredibly sensitive to perturbations. A small disturbance, a brief pulse of light or a slight change in magnetic field, can create waves that propagate through the condensate, reflecting off edges, interfering with themselves, creating complex patterns. These collective excitations, called quasi-particles, behave like particles themselves but are really just organized patterns in the coherent quantum field. One particularly beautiful example involves creating two separated Bose-Einstein condensates and studying their quantum tunneling. If the two condensates are brought close together but kept in separate traps, atoms can quantum mechanically tunnel from one condensate to the other. Because the condensates are phase coherent, this tunneling occurs collectively. Large numbers of atoms tunnel together, synchronized by their shared quantum state. The result is Josephson oscillations, periodic exchanges of atoms between the two condensates, named after Brian Josephson, who predicted similar oscillations in superconductors. These Josephson oscillations are purely quantum phenomena. There's no classical analogue, no way to understand them without invoking wave functions, phase coherence, and quantum tunneling. They demonstrate that the entire condensate, containing thousands or millions of atoms, behaves as a single quantum object, exhibiting coherent quantum behavior at scales far larger than anything possible at higher temperatures. Researchers have also used Bose-Einstein condensates to explore entanglement, a spooky connection between quantum objects that Einstein found so troubling. In an entangled state, measuring one particle instantly affects the others, regardless of the distance between them. Creating and measuring entanglement in condensates is challenging, but it's been done, demonstrating that macroscopic quantum objects can exhibit the same non-local correlations that individual particles do. The quantum symphony of a Bose-Einstein condensate is more than just a scientific curiosity. It's a window into how quantum mechanics operates when given full control, unobscured by thermal noise and classical behavior. It shows that the wave function, often treated as a mathematical abstraction, is real and measurable. It demonstrates that quantum coherence can extend over macroscopic distances and involve enormous numbers of particles. It proves that the quantum world, far from being limited to microscopic scales, can manifest in ways we can directly observe and manipulate. And as researchers continue pushing toward colder temperatures and more exotic quantum states, the symphony becomes ever richer, revealing harmonies and counterpoints that even the theory of quantum mechanics hadn't fully anticipated. Light, in the vacuum of space, travels at roughly 300,000 kilometers per second, the ultimate speed limit of the universe. Nothing with mass can reach this speed, and nothing, not even information, can travel faster. This cosmic speed limit is one of the foundational principles of relativity, seemingly inviolable and absolute. Yet in certain ultra-cold atomic gases, physicists have managed to slow light down to a walking pace. And in some cases they've brought light to a complete stop, freezing a pulse of photons inside a cloud of atoms, only to release it later, intact and unchanged. This remarkable feat relies on a quantum phenomenon called electromagnetically induced transparency, or EIT. The basic idea is subtle but powerful. Normally, when light passes through a material, some wavelengths are absorbed strongly, others barely at all, depending on the material's atomic structure. But in EIT, A clever arrangement of laser beams can create a situation where a wavelength that would normally be absorbed passes through transparently instead. Here's how it works. Imagine atoms with 3 energy levels, a ground state, an intermediate state, and an excited state. A probe laser beam tuned to the transition between the ground and excited states would normally be absorbed as atoms jump to the excited state. But now add a second laser called the coupling laser, tuned to the transition between the intermediate and excited states. If both lasers are present with the right intensities and frequencies, quantum interference between the two excitation paths can create what's called a dark state, a quantum superposition where the atom can no longer absorb the probe light. The result is that the material, which should be opaque to the probe laser, becomes transparent. The light passes through but not unchanged. The quantum interference that creates transparency also dramatically slows down the light's group velocity, the speed at which pulses of light propagate. In carefully prepared ultra-cold atomic gases, this slowing can be extreme. Light that normally travels at 300,000 kilometers per second can be reduced to meters per second, or even centimeters per second. In 1999, Lean Howe and her colleagues at Harvard University demonstrated this effect spectacularly. They created a Bose-Einstein condensate of sodium atoms and used EIT to slow a pulse of light down to 17 meters per second, about 40 miles per hour. The pulse entered the condensate, slowed dramatically, crawled through the cloud of atoms and emerged from the other side, its shape and information content preserved. But Howe's group didn't stop there. In 2001, they managed to bring light to a complete stop. They sent a pulse of light into the condensate and then gradually turned off the coupling laser. As the coupling laser faded, the probe pulse slowed further and further until it stopped completely. Its information transferred into a quantum excitation of the atomic cloud. The pulse had been converted from photons into a matter wave. A coherent excitation spread across thousands of atoms. Then, by turning the coupling laser back on, they retrieved the pulse. The matter wave excitation converted back into photons, and the original pulse of light emerged from the condensate, travelling at full speed again. The light had been stored in the atoms for a fraction of a second, but the principle was clear. Light could be stopped and started using quantum coherence in ultra-cold gases. This ability to slow and stop light has profound implications in quantum information processing. One of the challenges is storing quantum states. Photons are excellent for transmitting quantum information over long distances. They travel fast and don't interact much with their environment, but they're difficult to store. You can't just put photons in a box and keep them. They get absorbed or scattered. But if you can convert photons into matter waves in a Bose-Einstein condensate or similar system, you can store quantum information in atomic states, which are much easier to hold on to. Researchers have demonstrated quantum memories using this principle, storing entangled photons in atomic clouds and retrieving them later with high fidelity. They've shown that quantum information can be transferred between light and matter, held for significant periods, and then transferred back without losing its quantum properties. This is a crucial step toward building quantum networks. Systems where quantum information can be transmitted over long distances using photons and stored at nodes using atoms. The slowing and stopping of light also provides a beautiful example of how quantum mechanics can create effects that seem impossible from a classical perspective. Light doesn't have a speed control. Photons don't have brakes. Yet through quantum interference and the coherent interaction between light and matter, we can manipulate light's speed dramatically, even bringing it to rest inside a cloud of atoms. These experiments demonstrate the power of ultra-cold atomic physics. At temperatures near absolute zero, matter exhibits quantum coherence over macroscopic scales, enabling effects that would be washed out by thermal noise at higher temperatures. Atoms become precise, controllable quantum systems. Light becomes malleable, its speed adjustable by changing laser intensities. The boundary between light and matter becomes permeable, with photons converting to atomic excitations and back again. And all of this happens because we've pushed so close to absolute zero that quantum mechanics dominates completely, that the wave nature of everything, light and matter alike, becomes the primary reality. The universe is cold. The average temperature of intergalactic space, far from any star or galaxy, is about 2.7 degrees Kelvin, just above absolute zero. This cosmic microwave background radiation, the afterglow of the Big Bang, permeates all of space, setting a temperature floor for the entire universe. Nowhere in the natural universe, as far as we know, is colder than this, except in our laboratories. In facilities around the world, physicists routinely create temperatures far colder than anything found in nature. They achieve microkelvin, nanokelvin, even picokelvin temperatures, trillionths of a degree above absolute zero. The coldest places in the universe, by far, are not in the emptiness of space, but in carefully controlled experimental chambers on Earth. Creating these extreme temperatures requires extraordinary effort. The process typically starts with laser cooling, a technique developed in the 1980s that won its inventors the Nobel Prize in 1997. Laser cooling exploits the Doppler effect and the momentum transfer from photons. Atoms moving toward a laser beam see the light Doppler shifted to higher frequency. By tuning the laser frequency carefully, you can arrange for atoms moving toward the beam to absorb photons and slow down, while atoms moving away see the light shifted out of resonance and don't absorb. With lasers pointing in multiple directions, you can cool atoms in all directions simultaneously. But laser cooling has limits. The absorption and emission of photons is random, and this randomness heats the atoms even as the systematic momentum transfer cools them. The balance between cooling and heating sets a minimum temperature called the Doppler limit, typically a few hundred microkelvin. To go colder requires different techniques. One approach is Sisyphus cooling, which uses specially arranged laser configurations and magnetic fields to create a periodic potential in which atoms lose energy as they climb potential hills. Another is evaporative cooling, analogous to how a cup of coffee cools when the hottest molecules evaporate from the surface. In atomic clouds, the hottest atoms are selectively removed, leaving the colder atoms behind to thermalize at lower temperature. Through careful evaporation, temperatures of nanokelvin or below can be reached. The coldest temperature ever achieved in a laboratory, as of the early 21st century, was around 500 picokelvin, created in a Bose-Einstein condensate experiment. At this temperature, atoms move at speeds of just millimeters per second. Their de Broglie wavelengths, the quantum mechanical wavelengths associated with their motion, are comparable to the size of the atomic cloud itself. They've entered a regime where quantum mechanics dominates completely, where classical concepts of particle motion barely apply. Creating these temperatures requires not just cooling techniques, but also isolation from the environment. Any stray magnetic field, any fluctuation in laser intensity, any vibration of the apparatus can add energy and warm the atoms. Ultra-cold experiments take place in highly controlled environments, often in vacuum chambers with shielding against magnetic fields and mounted on vibration-isolated optical tables. The International Space Station hosts an experiment called the Cold Atom Laboratory, which uses microgravity to create even colder temperatures and study Bose-Einstein condensates for longer periods. Without gravity pulling the atoms down, condensates can be held and observed for seconds or even minutes, rather than the fractions of a second possible in Earth-based labs. The lack of gravitational sag also allows condensates to be cooled further, as gravity itself is a source of potential energy that limits how cold atoms can get. These ultra-cold laboratories have become among the most sophisticated scientific instruments humanity has ever built. They combine atomic physics, optics, quantum mechanics, and precision engineering to create conditions that, while they exist nowhere naturally in the universe, reveal fundamental truths about how matter behaves when quantum effects dominate. And the applications extend beyond pure research. Ultra-cold atoms are used in atomic clocks, the most precise timekeeping devices ever created. The current generation of atomic clocks, using strontium or ytterbium atoms cooled to microkelvin temperatures and trapped in optical lattices, are so stable that they would gain or lose less than 1 second over the age of the universe. These clocks are used to test fundamental physics, search for variations in fundamental constants, and define the international standard for the second. Ultra-cold atoms are also the basis for atom interferometers, sensors that can measure gravity with extraordinary precision. These devices have applications in geodesy, mapping the Earth's gravitational field, in inertial navigation, providing position information without GPS, and in fundamental physics, testing the equivalence principle and searching for dark matter. Perhaps most excitingly, ultra-cold atoms are being explored as platforms for quantum computing and quantum simulation. By trapping atoms in optical lattices and manipulating their quantum states with lasers, researchers can create artificial materials with properties that can be controlled precisely. These quantum simulators allow physicists to study problems in condensed matter physics that are too complex to solve with conventional computers, exploring phases of matter that might not exist in any natural material. The coldest places in the universe, paradoxically created in the warm confines of Earth laboratories, have become windows into the quantum realm, tools for precision measurement, and playgrounds for exploring the possibilities of matter when stripped of thermal chaos and reduced to its quantum essence. Classical computers, the devices we use every day, process information as bits, binary digits that are either 0 or 1. Transistors switch between 2 voltage states, representing these bits, and complex logic gates combine bits to perform calculations. This digital approach has proven extraordinarily powerful, enabling everything from smartphones to weather forecasting to artificial intelligence. But quantum computers operate differently. Instead of bits, they use qubits, quantum bits that can be in a superposition of 0 and 1 simultaneously. This isn't just both at once in some classical sense, it's a quantum superposition, where the qubit exists in a combination of states until measured, and when multiple qubits are entangled, their states become correlated in ways that have no classical analogue. The information capacity and computational power of a quantum system scales exponentially with the number of qubits. This quantum advantage comes with a severe challenge: decoherence. Quantum superpositions and entanglement are fragile, easily disrupted by interactions with the environment. A stray photon, a fluctuating magnetic field, even a tiny vibration can cause a qubit to lose its quantum information, collapsing from a superposition into a definite classical state. The more qubits you have and the longer you need to maintain coherence, the more difficult the problem becomes. Temperature is one of the primary enemies of quantum coherence. At high temperatures, thermal energy causes random fluctuations that destroy quantum states. This is why many quantum computer architectures operate at temperatures close to absolute zero. Superconducting qubits, one of the leading approaches, typically operate at around 20 millikelvin, just 0.02 of a degree above absolute zero. At these temperatures, thermal energy is so low that qubits can maintain superposition and entanglement for times long enough to perform meaningful calculations. Superconducting qubits are circuits made from superconducting materials, usually aluminum or niobium, patterned into shapes that allow them to exhibit quantum behavior. A common design is the transmon, which consists of a capacitor connected to a Josephson junction, a thin insulating barrier sandwiched between 2 superconductors. Cooper pairs can tunnel through the junction, and by carefully designing the circuit parameters, the system can be made to behave as a 2-level quantum system, a qubit. These qubits are controlled using microwave pulses that flip them between states, create superpositions, and generate entanglement between qubits. The challenge is doing this with high fidelity, while keeping error rates low enough that quantum error correction, techniques for detecting and correcting mistakes without destroying quantum information, can function effectively. Companies like IBM, Google, and others have built superconducting quantum processors with dozens to hundreds of qubits. In 2019, Google claimed quantum supremacy, demonstrating that their 53-qubit processor could solve a specific problem faster than classical supercomputers. The problem was admittedly contrived, designed to be difficult for classical computers, but the achievement marked a milestone in quantum computing development. Other quantum computing approaches also benefit from cold temperatures. Trapped ion quantum computers, which use individual ions held in electromagnetic traps as qubits, operate at temperatures where the ion's motion is in the quantum ground state, typically millikelvin to microkelvin ranges. The ions are manipulated using laser pulses that couple their internal electronic states to their motional states, enabling quantum gates. Neutral atom quantum computers trap atoms in arrays of optical tweezers and use laser pulses to manipulate their quantum states. These systems often cool atoms to microkelvin temperatures using laser cooling and evaporative cooling techniques. The low temperatures ensure that atoms remain trapped and that their quantum states can be controlled precisely. Even quantum computers that operate at higher temperatures, like some photonic quantum computers that use single photons as qubits, benefit from low-temperature detectors. Superconducting nanowire single-photon detectors, cooled to a few degrees Kelvin, can detect individual photons with near-perfect efficiency and negligible dark counts, the false signals that plague room-temperature detectors. The push toward absolute zero in quantum computing isn't just about reducing thermal noise. Though that's crucial, it's also about accessing quantum regimes where matter behaves purely according to quantum mechanics, where the hardware itself operates using quantum effects like superconductivity and Bose-Einstein condensation. Quantum computers are, in a sense, macroscopic quantum machines, devices that harness quantum coherence and entanglement at scales large enough to be engineered and controlled. The future of quantum computing likely involves pushing even closer to absolute zero, creating systems with lower noise, longer coherence times, and larger numbers of qubits. Each improvement in temperature control, each reduction in environmental coupling, brings us closer to fault-tolerant quantum computers that can solve problems intractable for classical machines. And the applications, once quantum computers mature, could be transformative. Simulating quantum chemistry to design new materials and drugs, breaking cryptographic codes and creating unbreakable quantum encryption, optimizing complex systems from traffic flow to financial markets, machine learning algorithms that operate on quantum data. The field is still young, the challenge is immense, but the progress is real, driven in part by our ability to create and control matter at temperatures approaching the absolute limit of cold. While physicists on Earth create the universe's coldest temperatures in laboratories, nature has found its own way to produce quantum matter at cosmic scales. Inside neutron stars, the collapsed cores of massive stars that have exploded as supernovae, matter exists in states so extreme that quantum effects dominate despite temperatures of millions of degrees. A neutron star is roughly the mass of the Sun compressed into a sphere about 20 kilometers across, roughly the size of a small city. The density is extraordinary, around 1 billion tons per cubic centimetre. A teaspoon of neutron star matter would weigh as much as a mountain. At these densities, atomic structure breaks down completely. Electrons are squeezed into atomic nuclei, combining with protons to form neutrons, and the star becomes essentially a single giant atomic nucleus, held together by gravity. But the story doesn't end there. The neutrons in these stars, despite being pressed together at nuclear densities, are thought to form a superfluid in the star's interior. The mechanism is different from the superconductivity of electron pairs in metals, or the superfluidity of helium atoms. In neutron stars, neutrons pair up through nuclear forces, similar to how electrons pair in superconductors, but at energies and densities far higher. This neutron superfluidity was predicted in the 1950s by physicists applying the BCS theory of superconductivity to nuclear matter. The prediction was that Despite the intense pressure and high temperature, neutrons in the core would condense into a superfluid state. The temperature is high by terrestrial standards, millions of degrees, but low compared to the energy scales of nuclear interactions. In that sense, the neutrons are effectively, quote 2, evidence for superfluidity in neutron stars comes from observing their spin-down behaviour. Neutron stars rotate, sometimes very rapidly, and they gradually slow down over time as they emit electromagnetic radiation and particle winds. But occasionally, neutron stars exhibit sudden speed-ups called glitches, where the rotation rate increases suddenly before resuming its gradual decrease. The explanation involves the interaction between the superfluid interior and the solid crust. The crust, made of nuclei arranged in a crystalline lattice, rotates with the star. But the superfluid interior can rotate independently, and it tends to spin faster than the crust. When the difference becomes too large, vortices in the superfluid, quantized lines of circulation similar to those in superfluid helium, suddenly transfer angular momentum to the crust, causing a glitch. This behavior is consistent with superfluidity and provides indirect evidence that neutron star interiors are indeed superfluid. Some models also predict that neutron stars contain superconducting regions where protons, present in small quantities even in neutron-rich matter, form Cooper pairs and become superconducting. These superconducting protons would expel magnetic fields from the regions they occupy, similar to the Meissner effect in terrestrial superconductors. The interplay between superconducting protons, superfluid neutrons, and the star's intense magnetic field creates complex dynamics that influence how neutron stars cool and evolve. The cooling of neutron stars themselves is a window into their interior physics. Young neutron stars are extraordinarily hot, with surface temperatures exceeding 1,000,000 degrees. They cool primarily through neutrino emission from their interiors. The rate of cooling depends sensitively on whether the interior is superfluid and superconducting. Superfluidity suppresses certain neutrino emission processes, slowing the cooling rate. By observing the temperatures of neutron stars of different ages, astronomers can test models of nuclear superfluidity and superconductivity. Neutron stars represent the ultimate extreme of condensed matter physics, where gravity, nuclear forces, and quantum mechanics all play crucial roles. They're natural laboratories for studying matter under conditions we could never recreate on Earth, where quantum effects operate at nuclear densities and macroscopic scales simultaneously, and they remind us that the quantum phenomena we observe in our ultra-cold laboratories, phenomena like superfluidity and superconductivity, aren't confined to earthly experiments. They're fundamental features of matter that emerge whenever conditions allow quantum coherence to dominate, whether in liquid helium at 3 degrees Kelvin or in neutron star cores at millions of degrees, compressed to densities where nuclei touch. The universe, it turns out, is full of quantum behavior. We just need to know where to look. In 1964, 2 radio astronomers working at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to track down an annoying source of noise in their antenna. The noise was faint but persistent, a uniform hiss coming from all directions in the sky. They checked everything. They cleaned pigeon droppings from the antenna. They calibrated their equipment meticulously. The noise remained. What Penzias and Wilson had discovered, though they didn't initially realize it, was the cosmic microwave background radiation, the afterglow of the Big Bang. Photons that have been travelling through space for nearly 14 billion years, cooling as the universe expanded. This radiation has a temperature of about 2.7 degrees Kelvin, negative 270 degrees Celsius, just above absolute zero. This cosmic microwave background, or CMB, is the coldest naturally occurring thing in the universe. It's everywhere, filling all of space uniformly. Every cubic centimetre of intergalactic space contains about 400 CMB photons, remnants of the intense radiation that filled the early universe when it was hot and dense. As the universe expanded, this radiation cooled, shifting from visible light to infrared to microwaves, eventually reaching the low-energy microwave photons we detect today. The temperature of the CMB tells us about the universe's age and expansion rate. In the earliest moments after the Big Bang, the universe was extraordinarily hot, trillions of degrees, far too hot for atoms to exist. Matter was a plasma of free electrons and nuclei, and photons scattered constantly off the free electrons, creating an opaque fog. But as the universe expanded and cooled, eventually it reached a temperature around 3000 degrees Kelvin, cool enough for electrons to combine with nuclei and form neutral atoms. This recombination event, occurring about 380,000 years after the Big Bang, made the universe transparent. The photons that were last scattered at recombination have been travelling freely ever since, cooling along with the universe's expansion. Measuring the CMB precisely has been one of the great achievements of modern cosmology. The COBE satellite in the early 1990s, Biomap in the 2000s, and Planck in the 2010s mapped the CMB's temperature across the entire sky with ever-increasing precision. These measurements revealed tiny fluctuations in temperature, about 1 part in 100,000, that correspond to density variations in the early universe. These density variations were the seeds from which galaxies, stars and planets eventually formed. The CMB's temperature also sets a lower limit for how cold anything in the universe can naturally be. Any object in intergalactic space, no matter how isolated, will eventually reach equilibrium with the CMB at 2.7 Kelvin. You can't get colder than the universe itself unless you actively remove energy, which is why the ultra-cold temperatures achieved in laboratories, temperatures billions of times colder than the CMB, require such extraordinary effort. But the CMB temperature hasn't always been 2.7 Kelvin. In the early universe, when the cosmos was smaller and denser, the CMB was hotter. At recombination, it was 3000 degrees. At 1 second after the Big Bang, it was roughly 10 billion degrees, and the CMB will continue cooling as the universe expands. 1 trillion years from now, its temperature will be less than 1 degree Kelvin. Eventually, in the far future, it will approach, but never quite reach absolute zero. This gradual cooling of the universe is part of a broader trend toward equilibrium and maximum entropy. The second law of thermodynamics says that entropy, roughly speaking, the amount of disorder in a system, always increases in closed systems. The universe as a whole is the ultimate closed system, and its entropy has been increasing since the Big Bang. Stars form and shine, but eventually they exhaust their fuel. Black holes form and slowly evaporate through Hawking radiation. The available energy for doing work gradually decreases. In the extremely distant future, trillions upon trillions of years from now, cosmologists predict a scenario called heat death, where the universe reaches maximum entropy. All matter will have decayed or fallen into black holes, and even the black holes will have evaporated. The universe will be a dilute sea of particles and radiation, are nearly uniform in temperature, incredibly close to absolute zero, with almost no structure or organisation remaining. This ultimate fate of the universe is sometimes called the Big Freeze, and it represents a kind of absolute zero for the cosmos itself, not just in temperature but in activity, complexity and possibility. It's a thought that can seem bleak, this inevitable slide toward cold uniformity. But that fate is so far in the future, vastly longer than the universe's current age, that it's more a philosophical meditation than a practical concern. For now, the universe is young, active, full of stars and galaxies and life. The cosmic microwave background bathes all of space in cold radiation, a reminder of the universe's hot birth and its ongoing expansion. And that radiation, at 3 degrees above absolute zero, is the natural temperature of the cosmos, the background against which all other temperatures are measured. As we've journeyed toward absolute zero, exploring superfluids and superconductors, Bose-Einstein, condensates and slowed light, neutron stars and cosmic background radiation, certain patterns have emerged, themes that repeat across different phenomena, insights that unify our understanding of how matter behaves when quantum mechanics dominates. The first pattern is coherence. At high temperatures, matter is incoherent. Atoms move randomly, their quantum phases scrambled by thermal fluctuations. But at low temperatures, quantum coherence emerges. Wave functions begin to overlap, phases lock together, many particles condense into single quantum states. This coherence enables the macroscopic quantum phenomena we've encountered, from superfluidity to superconductivity to Bose-Einstein condensation. It's the emergence of order from quantum mechanics, a kind of self-organization driven by the fundamental rules of quantum statistics and wave function overlap. The second pattern is collective behavior. At absolute zero, particles stop acting as individuals and start acting as collectives. Cooper pairs in superconductors don't move independently. They move together, coordinated by their shared quantum state. Helium atoms in superfluid helium flow as a single entity, not a collection of separate atoms. This collectivity is what makes these states so different from ordinary matter. Classical physics treats particles as distinguishable individuals whose behavior can be understood separately. Quantum mechanics at low temperatures demands treating them as inseparable parts of a larger whole. The third pattern is universality. Many of the phenomena we've discussed occur in very different physical systems, but exhibit similar behavior. Superfluidity appears in liquid helium, in neutron stars, and in ultra-cold atomic gases, despite these systems having wildly different densities, temperatures, and constituent particles. Superconductivity occurs in conventional metals via electron-phonon coupling, and in exotic ceramics through mechanisms we still don't fully understand, yet both exhibit zero resistance and the Meissner effect. This universality suggests that these phenomena arise from deep principles of quantum mechanics that transcend the details of specific materials. The fourth pattern is simplicity through cooling. This might seem paradoxical. How can cooling to absolute zero, which reveals bizarre quantum behaviors, be considered simplification? But in a sense, it is. At high temperatures, matter's behavior is complex because thermal fluctuations create randomness and disorder. Many competing effects occur simultaneously. But at low temperatures, thermal energy becomes negligible, and only the quantum ground state and low-lying excited states matter. The system's behavior becomes determined by its fundamental quantum properties rather than by thermal noise. In this sense, absolute zero is where matter becomes most itself, where its essential quantum nature is fully revealed. The fifth pattern is the interplay between theory and experiment. Almost every phenomenon we've discussed was predicted theoretically before being observed experimentally, sometimes decades before. Bose-Einstein condensation was predicted in 1924, but not observed until 1995. Superfluidity was observed before being understood, but required quantum field theory to fully explain. The third law of thermodynamics, stating that absolute zero is unreachable, was formulated before the quantum mechanical reasons were understood. This back and forth between theoretical prediction and experimental verification is how physics advances, each side informing and challenging the other. And perhaps the most profound pattern is emergence. The phenomena of superfluidity, superconductivity, and Bose-Einstein condensation aren't programmed into the universe at a fundamental level. They emerge from the collective behavior of many particles obeying simple quantum mechanical rules. You can't understand superfluidity by studying a single helium atom, just as you can't understand consciousness by studying a single neuron. These are emergent phenomena, properties of complex systems that arise from but aren't reducible to the properties of their components. This emergence is central to modern physics. The standard model of particle physics describes fundamental particles and forces with impressive precision, but it doesn't directly predict the behavior of liquid helium or high-temperature superconductors. Those require condensed matter physics, the study of how large numbers of particles behave collectively. And condensed matter physics has revealed that complexity and novel behaviour emerge at every level, from atoms to molecules to materials to biological systems. What we've learned from studying matter at absolute zero is that the universe is layered. Each layer has its own principles, its own phenomena, its own kinds of explanation. And each layer is real and important. The quantum mechanics of individual atoms matters. The statistical mechanics of many atoms also matters. The emergent collective behaviour matters too. None of these levels is more fundamental or real than the others. They're all part of the complete picture, and that picture, as we've seen, is strange and beautiful. It's a universe where liquids can flow uphill, where electricity can flow forever without power, where thousands of atoms can merge into single quantum objects, where light can be stopped and stored and released again. A universe where the coldest temperatures reveal the most profound truths about matter's quantum nature. As we move toward our final chapters, we'll contemplate what these discoveries mean philosophically and cosmically. We'll think about time and entropy and the structure of physical law. We'll consider why cold matters, not just scientifically but existentially. And we'll end where we began, with wonder at the strangeness that emerges when we push matter to its limits. Time, as we experience it, flows in one direction. The past is fixed, the future uncertain. This arrow of time seems fundamental to our existence, yet it's not present in most of physics' fundamental laws. The equations of classical mechanics work equally well forward or backward in time. The laws of quantum mechanics are time reversible. Even Einstein's general relativity, which describes gravity and the fabric of space-time itself, treats past and future symmetrically. Yet the arrow of time is real. Eggs break but don't spontaneously reassemble. Mixed coffee and cream don't separate back into distinct layers. Heat flows from hot to cold, never the reverse without external work. This directional flow of time arises from the second law of thermodynamics. Entropy, the measure of disorder in a system, always increases in closed systems, and it's at temperatures approaching absolute zero that the relationship between time, entropy, and quantum mechanics becomes most clear. Entropy is fundamentally a measure of possibilities, of the number of microstates, particular arrangements of atoms and energy, that correspond to a given macrostate, the overall properties we observe. A gas of randomly moving atoms has high entropy because there are countless indistinguishable ways to arrange the atoms that produce the same overall pressure and temperature. A perfect crystal at absolute zero has low entropy because there's essentially only one arrangement, all atoms in their ground states in perfectly ordered positions. The third law of thermodynamics states that the entropy of a perfect crystal approaches zero as the temperature approaches absolute zero. This makes intuitive sense. At absolute zero, thermal motion ceases, leaving only zero-point quantum fluctuations. The system settles into its ground state, the single lowest energy configuration. There's no thermal disorder, no random motion, no ambiguity about the system's microstate. But achieving absolute zero would require infinite time or infinite effort, according to the third law. As you cool a system, each further degree of cooling becomes harder. You're not just removing energy, you're removing entropy, fighting against the second law's tendency for disorder to spread throughout the universe. The third law essentially says that complete order, zero entropy, is unattainable, just as absolute zero temperature is unattainable. This connection between temperature and entropy reveals something deep about time itself. The arrow of time, the fact that we remember the past but not the future, that cause precedes effect, that entropy increases, all derive from the second law. And the second law arises from statistics. Given a system that could be in many different microstates, it's overwhelmingly more likely to be in a high entropy state simply because there are more ways to be disordered than ordered. But at absolute zero, this statistical argument changes character. There's only one ground state, or sometimes a small number of degenerate ground states so entropy is minimal. Time's arrow, in some sense, softens. A quantum system in its ground state doesn't spontaneously change. It has nowhere lower to go, no disorder to increase. It can only change if energy is added or if it interacts with another system. This has profound implications for quantum systems. The systems we've discussed, Bose-Einstein condensates, superconductors, superfluids, persist in their quantum states indefinitely unless disturbed. A persistent current in a superconducting loop doesn't decay with time. It continues forever, or at least until something breaks the superconductivity. The system has reached a state of minimum energy and entropy, and it simply stays there. In philosophical terms, absolute zero represents a kind of timelessness. Not the absence of time, but the absence of time's arrow. A system at absolute zero, if such a thing could exist, wouldn't change spontaneously. It would be static, eternal, unchanging. This contrasts sharply with our experience of time as flow, as change, as irreversible progression from past to future. Some physicists and philosophers have speculated about the connection between time, entropy, and consciousness. Our subjective experience of time's flow might arise from our brain's thermodynamic processes, from the continual increase of entropy in neural states as we process information and form memories. If so, consciousness requires entropy increase, requires thermal motion, requires temperatures well above absolute zero. A mind, if such a thing could exist at absolute zero, might experience no passage of time at all. These are speculative thoughts, ventures into philosophy that physics can inform but not definitively answer. But they illustrate how the study of ultra-low temperatures touches on questions far beyond material properties. It reaches toward the nature of time, the origin of the second law, the possibility of eternal states in a universe that generally trends toward disorder and heat death. And there's a poignant beauty in this connection. The coldest temperatures, where matter behaves most strangely and quantum mechanics reigns supreme, are also the temperatures where time's relentless march slows, where entropy's increase pauses, where something approaching permanence becomes possible. In a universe that's constantly changing, constantly aging, constantly moving toward maximum disorder, the quantum states at absolute zero offer a glimpse of stillness, of states that could, in principle, last forever. The third law of thermodynamics is stated simply: as the temperature of a system approaches absolute zero, the entropy approaches a minimum value, and absolute zero itself cannot be reached through any finite sequence of operations. This law, less famous than the first and second laws but equally fundamental, places a hard limit on our quest for cold. The impossibility of reaching absolute zero isn't a matter of technological limitation, it's a matter of principle, woven into the structure of thermodynamics and quantum mechanics. Every cooling method, no matter how clever, eventually runs into the third law's constraint. You can get arbitrarily close, reaching picokelvin or even femtokelvin temperatures in principle, but you can never quite reach zero. Why is this? The answer lies in how cooling works. To cool something, you must remove energy from it, transferring that energy to something else. But as a system gets colder, the available energy states become more sparse. At very low temperatures, quantum mechanics plays a crucial role. The energy levels are quantized, discrete rather than continuous. The lowest energy state, the ground state, has finite energy due to zero-point fluctuations. Moreover, cooling requires contact, either physical or through radiation, with a colder reservoir. But if your system is already at near absolute zero, there's no colder reservoir available. You'd need to cool your cooling system first, which requires an even colder system, and so on, infinitely. It's impossible to bootstrap your way to absolute zero. Another perspective comes from the Heisenberg uncertainty principle. To localize a particle perfectly in momentum space, to bring it to exactly zero momentum, would make its position completely uncertain, infinitely spread out in space. This costs infinite energy. So even the act of bringing a particle to rest violates quantum principles unless the particle retains some zero-point motion. Yet despite its unattainability, absolute zero serves as a crucial theoretical reference point. It's the limiting case where all thermal motion vanishes and only quantum effects remain. Extrapolating to absolute zero allows physicists to understand material properties at low temperatures, to predict behaviours, to test theories. The third law gives this extrapolation rigour, ensuring that entropy and other thermodynamic quantities have well-defined limits as temperature goes to zero. The third law also has practical implications. It means that achieving each successive reduction in temperature requires exponentially more effort. Cooling from 100 degrees Kelvin to 10 degrees is much easier than cooling from 10 degrees to 1 degree, which is in turn much easier than cooling from 1 degree to 0.1 degrees. This scaling makes ultra-low temperature physics technically challenging and expensive, but there's a philosophical dimension too. The third law tells us that perfection is unattainable. Just as we can never measure a particle's position and momentum with infinite precision, just as we can never transmit information faster than light, we can never cool an object to absolute stillness. The universe has built-in limits, boundaries that constrain what's possible. These limits aren't defects or failures of our knowledge, they're features of reality itself. Some find this frustrating, a cosmic no trespassing sign barring us from a realm we'd like to explore. But there's another way to see it. The limits imposed by physical law are what give the universe structure. Without conservation laws, without speed limits, without thermodynamic boundaries, physics would be arbitrary chaos. The constraints are what make the universe lawful, predictable, comprehensible. And in the case of absolute zero, the very impossibility of reaching it tells us something profound about quantum mechanics. The fact that zero-point energy exists, that motion persists even at the lowest possible temperature, reveals that the quantum world is fundamentally restless. There's no such thing as perfect stillness at the quantum level. Everything vibrates, fluctuates, moves at least a little forever. This quantum restlessness is, in a way, comforting. It means the universe is never truly dead, never truly static. Even in the far future, when the universe has cooled to nearly absolute zero and entropy has reached its maximum, quantum fluctuations will persist. Virtual particles will appear and vanish in the vacuum. Fields will oscillate around their ground states. The universe will never be perfectly still, perfectly uniform, perfectly done. The third law, then, is both a limitation and a promise. It tells us we cannot reach absolute zero, but also that the universe remains quantum, dynamic, and full of subtle activity even at the lowest temperatures. It's a boundary that defines the edge of possibility while simultaneously revealing that even at that edge, the universe retains its essential nature. And as we approach our final chapters, having explored the science of absolute zero in depth, we'll turn to broader questions. Why does cold matter? What do these discoveries mean for humanity's future? What beauty lies in the quantum strangeness revealed at the universe's coldest temperatures? These aren't purely scientific questions. They're questions about meaning, about purpose, about why we explore the universe's extremes even when we can never quite reach them. When we think of vacuum, we imagine emptiness. A space with nothing in it, no particles, no energy, no activity. But quantum mechanics tells a different story. The vacuum, even when cooled to absolute zero and drained of every particle, isn't empty. It seethes with activity at scales so small and times so brief that we can barely detect them. This activity arises from the same uncertainty principle that prevents atoms from being perfectly at rest. The uncertainty principle applies not just to particles but to fields, the fundamental entities that permeate all of space. The electromagnetic field, for instance, has quantum fluctuations. Even in regions of space with no photons, no light, no electromagnetic radiation, the field fluctuates, creating virtual photons that appear and disappear too quickly to violate conservation of energy. These vacuum fluctuations are sometimes called quantum foam, a term coined by physicist John Wheeler. He imagined that if you could look at space-time at the Planck scale, distances of about 10 to the minus 35 meters, you'd see a roiling sea of fluctuations. Geometry itself bubbling and frothing with quantum uncertainty. At larger scales, these fluctuations average out to smooth space-time, but at the smallest scales, quantum mechanics makes space-time itself uncertain and dynamic. One consequence of vacuum fluctuations is the Casimir effect, which we mentioned earlier. Two uncharged metal plates placed close together in a vacuum experience an attractive force because the vacuum between the plates has fewer possible quantum fluctuations than the vacuum outside. The difference in zero-point energy creates measurable pressure. This effect has been precisely measured and confirms that vacuum fluctuations are real. Another consequence is spontaneous emission. An excited atom in an isolated system will eventually decay to its ground state, emitting a photon. But what causes the decay? In quantum field theory, the answer is vacuum fluctuations. The electromagnetic vacuum isn't really empty, it's filled with virtual photons. These virtual photons interact with the excited atom, stimulating it to emit a real photon. Without vacuum fluctuations, atoms in excited states would stay excited indefinitely. Vacuum fluctuations also play a role in particle physics. The mass of fundamental particles isn't just an intrinsic property. It's modified by interactions with virtual particles. An electron, for instance, constantly emits and reabsorbs virtual photons, and this process contributes to the electron's observed mass and charge. Calculating these effects requires sophisticated techniques from quantum field theory, but the results agree with experiments to extraordinary precision. In cosmology, vacuum energy, sometimes called dark energy, is thought to be driving the universe's accelerated expansion. Observations of distant supernovae show that the expansion is speeding up, not slowing down as gravity alone would predict. The simplest explanation is that space itself has a small positive energy density, a cosmological constant that acts like a repulsive force. This vacuum energy might be related to the zero-point energy of quantum fields, though there's a notorious problem. Naive calculations predict a vacuum energy density vastly larger than observed, a discrepancy called the cosmological constant problem. These connections between vacuum fluctuations and physical phenomena demonstrate that the quantum vacuum is far from empty. It's a reservoir of energy and activity, constrained by the uncertainty principle to perpetual restlessness. And this restlessness persists even at absolute zero. You could cool the universe to the lowest possible temperature, remove every particle, and the vacuum would still fluctuate, still produce virtual particles, still have zero-point energy. This leads to a striking realization. Absolute zero, the state we've been approaching throughout this journey, isn't a state of nothingness. It's a state where thermal energy vanishes but quantum energy remains. It's the ground state of matter and energy, but the ground state is active, vibrant, full of quantum possibilities. The universe, even at its coldest, never truly rests. There's something almost comforting in this. The restless quantum vacuum means that even in the far future, when the universe has cooled and expanded to near absolute zero, when stars have all burned out and black holes have all evaporated, the vacuum will still be alive with quantum fluctuations. The universe will never be truly dead, truly empty, truly still. It will always retain a kind of quantum vitality, a baseline of activity that can never be removed, and this vitality, this perpetual quantum motion, is part of what makes reality possible. Without vacuum fluctuations, atoms wouldn't decay, particles wouldn't have mass, the universe would be fundamentally different. The restless quantum vacuum isn't a flaw or imperfection, it's a feature essential to the universe's structure and stability. Throughout this journey, we've explored the science of ultra-low temperatures, discovering phenomena that seem impossible yet are real and measurable. But a natural question arises. Why does this matter? Why should we care about superfluids and Bose-Einstein condensates, about quantum computers operating at millikelvin temperatures, about laboratories creating the coldest places in the universe? The most immediate answer is practical applications. The technologies enabled by ultra-cold physics are already transforming our world. Superconducting magnets in MRI machines save lives by allowing doctors to see inside the body without surgery. Atomic clocks based on ultra-cold atoms keep time with precision that enables GPS navigation, accurate to within meters anywhere on Earth. Quantum sensors using atom interferometry measure gravity, magnetic fields, and accelerations with unprecedented sensitivity, with applications in mineral exploration, earthquake detection, and fundamental physics tests. But the potential future applications are even more significant. Quantum computers, when they mature, could revolutionize drug discovery by simulating molecular interactions that classical computers cannot handle. They could optimize complex logistics, from supply chains to traffic flow to energy grids, saving enormous resources. They could break current encryption schemes, but also enable quantum encryption that's theoretically unbreakable, and they could accelerate machine learning, allowing AI systems to process quantum data directly. High-temperature superconductors, if developed to work at more accessible temperatures and with sufficient current carrying capacity, could transform electrical transmission. Current power grids lose about 5 to 10% of electrical energy to resistance in transmission lines. Superconducting lines would lose nothing, making renewable energy sources like wind and solar more viable by enabling efficient long-distance transmission from generation sites to population centres. Beyond technology, ultra-cold physics provides testing grounds for fundamental theories. Bose-Einstein condensates allow researchers to study quantum phase transitions, points where matter changes abruptly from one quantum state to another. These transitions have analogues in particle physics and cosmology, in phenomena we can never directly access, like the quark-gluon plasma of the early universe or the interior of neutron stars. By creating analogues in ultra-cold gases, we can test theories and gain insights that inform our understanding of the cosmos. Ultra-cold atoms also provide platforms for quantum simulation, using one quantum system to simulate another. Some problems in physics, like understanding high-temperature superconductivity or modelling complex molecules, are too difficult for classical computers to solve exactly. They involve too many interacting quantum particles with too many possible states. But an ultra-cold atomic system, with its controllable interactions and observable quantum states, can be tuned to mimic the system you want to study. You can then measure the atomic system's behaviour and learn about the system it's simulating. There's also a philosophical dimension to why cold matters. Studying the universe's extremes, whether the hottest temperatures in particle accelerators or the coldest temperatures in atomic physics labs, pushes the boundaries of our knowledge. It tests theories, reveals unexpected phenomena, and often opens entirely new fields of inquiry. The history of science is full of examples where exploring extremes led to revolutionary discoveries. Superconductivity, discovered while exploring cold, took nearly 50 years to explain, and led to technologies that now underpin modern medicine and research. And there's simple human curiosity. We explore cold temperatures for the same reason we explore space, the deep ocean, the human genome. Because they're there. Because we can. Because understanding the universe in all its diversity and strangeness is a fundamental human drive. The discoveries we make often surprise us, leading in directions we never anticipated. Who could have predicted when Camelignons first liquefied helium in 1908 that this would eventually lead to quantum computers? Science is unpredictable. We explore because we don't know what we'll find. Perhaps most importantly, ultra-cold physics reveals beauty. There's something aesthetically compelling about matter behaving according to quantum mechanics at scales we can see and touch. A levitating magnet, a liquid climbing walls, light brought to a standstill. These phenomena are beautiful not just in their visual appearance but in their conceptual elegance. They show us that the universe operates according to principles that, while strange, are comprehensible and beautiful in their mathematical structure. Cold matters because it's where the universe reveals its quantum nature most clearly. It's where we can study the fundamental laws of physics without the obscuring effects of thermal noise. It's where matter behaves in ways that challenge our intuitions and expand our understanding. And it's where the boundary between physics, technology and philosophy becomes permeable, where practical applications, theoretical insights and existential questions all intersect. As we move toward our final chapters, we'll reflect on the beauty and meaning of what we've discovered. We'll think about humanity's place in a quantum universe, and we'll find, perhaps surprisingly, that the coldest temperatures offer not just scientific knowledge, but a kind of cosmic perspective. A way of understanding our connection to the universe at its most fundamental level. There's a peculiar aesthetic quality to the mathematics and physics of absolute zero. The equations simplify, thermal noise vanishes, complex behaviours reduce to their essential quantum mechanical cause. In some sense, absolute zero is where physics becomes most beautiful because it becomes most pure. Consider the Schrödinger equation, the fundamental equation of quantum mechanics that describes how quantum systems evolve in time, at high temperatures. Solving this equation for real materials is extraordinarily difficult. Thermal energy means particles are in many different quantum states, all mixed together. The wave function is complex, the possible states numerous. But at absolute zero in the ground state, the mathematics becomes more tractable. The system is in its lowest energy state, described by a single wave function, and many calculations that would be impossible at higher temperatures become feasible. This simplification isn't just computational convenience, it reflects a deep truth about nature. Complexity, in many systems, arises from disorder and randomness introduced by temperature. Strip that away, and the underlying order becomes visible. A crystal at absolute zero has perfect translational symmetry, every atom in its proper place. Liquid helium becomes a superfluid with a single macroscopic wave function. Electrons pair up and condense into a superconducting state describable by simple quantum mechanical principles. Physicists often speak of elegance in theories and phenomena. An elegant theory explains much with little, unifying diverse phenomena under simple principles. The equations of general relativity are elegant, compressing the behaviour of gravity, space-time and the large-scale structure of the universe into a concise mathematical statement. Maxwell's equations are elegant, describing all of electricity and magnetism in four fundamental relations. The phenomena at absolute zero share this elegance. Superfluidity, superconductivity, Bose-Einstein condensation all arise from the same basic quantum principles: wave function coherence, quantum statistics, and the minimization of energy. Different materials, different particles, different physical contexts, but the underlying physics is similar. This universality, this commonality across diverse systems, is what physicists mean by beauty in science. There's also a visual beauty to many low-temperature phenomena. The symmetry of vortex lattices in rotating Bose-Einstein condensates. The perfect mirror reflection from superconductors expelling magnetic fields. The interference patterns created when matter waves overlap. These aren't just beautiful to look at. They're beautiful because they're direct visualizations of quantum mechanics at work. You're literally seeing the mathematical structure of quantum theory rendered in physical form. Philosophy has long recognized beauty as a guide to truth. Keats wrote that beauty is truth, truth beauty, and while this might overstate the case, there's something to it in physics. Theories that work, that accurately describe nature, often have a simplicity and elegance that feels beautiful. Einstein trusted this principle, famously saying that the theory should be as simple as possible but no simpler. When faced with competing theories that both fit the data, physicists often prefer the more elegant one, the one with fewer assumptions and more explanatory power. Ultra-cold physics exemplifies this connection between beauty and truth. The phenomena are beautiful, both visually and conceptually. The mathematics is elegant, reducing complex behavior to simple quantum principles. And the theories work, making predictions that experiments confirm with high precision. This confluence of beauty, simplicity, and accuracy isn't coincidental. It's a sign that we're touching something deep about the universe's structure. But there's a deeper aesthetic dimension too, one that's harder to articulate. It has to do with the way absolute zero represents a kind of limit, a boundary that defines the possible. Just as infinity in mathematics gives structure to the concept of limits and boundedness, absolute zero gives structure to the concept of temperature and thermal energy. It's the 0 point, the reference against which all other temperatures are measured. And there's something satisfying, something aesthetically pleasing, about systems that approach such fundamental limits. Perhaps this is because limits, in mathematics and physics, are often where interesting behaviour emerges. Phase transitions occur at specific temperatures. Singularities in equations often indicate new physics. Limits force us to think carefully about approximations and assumptions. And absolute zero is the ultimate limit for temperature. The point where classical thermal physics gives way entirely to quantum mechanics. This interplay between classical and quantum, between the everyday world and the bizarre quantum realm, is part of what makes ultra-cold physics compelling. It's a bridge between two ways of understanding reality. At room temperature, we can mostly ignore quantum mechanics for everyday phenomena. Matter behaves classically, predictably, in accord with our intuitions. But at absolute zero, quantum mechanics is unavoidable. It's the only game in town. And yet, remarkably, we can create these quantum conditions, study them, manipulate them. We can bring the bizarre quantum world into our laboratories and see it with our own eyes. There's a kind of privilege in this. For most of history, humans had no idea that matter behaved quantum mechanically. The quantum world was hidden, inaccessible, unknowable. But in the last century, we've peeled back that veil. We've learned to create conditions where quantum effects dominate. We've built technologies that exploit quantum principles. We've gained a window into the fundamental nature of reality, and what we see through that window is beautiful. Strange, yes. Counterintuitive, certainly, but beautiful in its structure, its simplicity, its elegance. Absolute zero represents not an end but a beginning, the starting point for understanding matter's quantum nature. And in that quantum nature, revealed most clearly at the coldest temperatures, we find patterns and principles that unify our understanding of the physical world. The universe began hot, unimaginably so. In the first fraction of a second after the Big Bang, temperatures exceeded trillions of degrees. Matter as we know it couldn't exist. Even fundamental particles like protons and neutrons hadn't formed. The universe was a plasma of quarks and gluons, energy and matter in their most elementary form. But the universe has been cooling ever since. As it expanded, temperatures dropped. Within microseconds, quarks combined into protons and neutrons. Within minutes, protons and neutrons fused into the first atomic nuclei, mostly hydrogen and helium. Within hundreds of thousands of years, the universe cooled enough for electrons to combine with nuclei, forming the first neutral atoms. This cooled universe, at about 3000 degrees Kelvin, released the cosmic microwave background radiation that we still detect today, now cooled to 3 degrees above absolute zero. In a profound sense, everything we are, every atom in our bodies, every structure in the universe, emerged through cooling. Stars formed from collapsing clouds of hydrogen and helium, compressed and heated by gravity until nuclear fusion ignited. In those stellar furnaces, hydrogen fused into helium, helium into carbon and oxygen, and in the cores of the most massive stars, elements up to iron formed. When these stars exploded as supernovae, even heavier elements were created in the intense heat and pressure of the explosion, but these elements scattered into space, cooled. They mixed with interstellar gas and dust, forming new clouds that eventually collapsed to form new stars and planets. Our solar system formed this way 4.5 billion years ago, from the cooled remnants of earlier stellar generations. Every atom heavier than hydrogen in your body was forged in a star and cooled in the depths of space, before eventually finding its way into the molecular clouds that formed our Sun and Earth. Earth itself has been cooling for billions of years. Early Earth was molten, its surface a sea of magma, heated by the energy of accretion, the collisions of countless planetesimals during the solar system's formation. But gradually heat radiated into space. The surface cooled and solidified, forming the first crust. Volcanic outgassing released water vapour that condensed into liquid water once the surface was cool enough. Oceans formed, the atmosphere evolved, and in those oceans, in the chemical richness enabled by liquid water at moderate temperatures, life emerged. Life too depends on temperature. Too hot and complex molecules break apart. Too cold and chemical reactions slow to a crawl. Life as we know it exists in a narrow temperature range, roughly 0 to 100 degrees Celsius, where water is liquid and biochemistry operates efficiently. We are fundamentally creatures of moderate temperatures, dependent on the cooling that allowed stable chemistry and complex organization to emerge. But our origins trace back to the cooling of the universe itself. The Big Bang's initial inferno produced only the lightest elements. The complex chemistry necessary for life required stellar nuclear synthesis, the fusion of lighter elements into heavier ones in stellar interiors, and that chemistry could only become organized into living systems after the universe had cooled sufficiently for planets and liquid water to exist. In this sense, we are children of the universe's long cooling. The atoms in your body, the carbon in your cells, the oxygen you breathe, the iron in your blood, all formed in stars and cooled over billions of years. The structure of your DNA, the proteins that make your muscles contract and neurons fire, all depend on molecular bonds that would break in the primordial heat. You exist because the universe cooled, and the universe is still cooling. The cosmic microwave background temperature decreases as the universe expands. In the distant future, it will approach absolute zero. Stars will exhaust their fuel, galaxies will darken. Eventually, even black holes will evaporate through Hawking radiation, returning their mass energy to space in the form of particles and radiation. The universe trends toward cold, toward maximum entropy, toward a state where temperature becomes negligible and structure dissolves. This might seem bleak, this inevitable cooling toward nothingness. But there's another way to see it. The cooling of the universe is what enabled structure to form in the first place. In the initial hot plasma, no atoms could exist, no molecules, no stars or planets, or life. Structure requires temperature gradients, regions of different energy that can interact and organize, and temperature gradients require overall cooling. Moreover, our existence represents an extraordinary moment in cosmic history. We live in an era when stars shine, when galaxies swirl, when planets harbour life. This era is vast by human standards, lasting trillions of years, but it's finite. Before it, the universe was too hot for complexity. After it, the universe will be too cold and diffuse. We exist in the brief window when structure and complexity are possible. And perhaps that's enough. To be part of this cosmic story, to arise from stardust and understand, even partially, the processes that created us, to push toward absolute zero in our laboratories and discover the quantum nature of matter, all of this is remarkable. We are the universe contemplating itself, matter organized into forms complex enough to wonder about their origins and fate. The coldest temperatures, the realm of quantum mechanics and ultra-low thermal energy, are where we find the universe's most fundamental behaviors. But those behaviors enabled everything else. The quantum mechanics that dominates at absolute zero also governs atomic structure, chemical bonding, the stability of matter. Without quantum mechanics, atoms wouldn't exist as stable structures. Without atomic structure, chemistry wouldn't work. Without chemistry, life couldn't form. So when we study absolute zero, when we create Bose-Einstein condensates and superconductors, when we push matter to its quantum limits, we're not just exploring an exotic corner of physics, we're exploring the foundation of everything, the quantum mechanical substrate that makes reality possible. We're connecting the coldest temperatures to the hottest origins, the simplest quantum states to the most complex living systems. We've travelled far in this exploration, from room temperature down toward absolute zero, encountering phenomena that challenge our everyday understanding of matter and motion. We've seen liquids that climb walls, metals that conduct electricity forever, atoms that merge into single quantum entities. We've watched light slow to a standstill and contemplated the quantum vacuum's perpetual restlessness. And through it all, a central theme has emerged. Absolute zero is not emptiness or nothingness, but a state where matter reveals its essential quantum nature. The phrase, the still point, comes from T.S. Eliot, who wrote in Burnt Norton, at the still point of the turning world, neither flesh nor fleshless, neither from nor towards, at the still point, there the dance is. Eliot wasn't writing about physics, but his words capture something about absolute zero. It's a point of stillness, yet not truly still. A place where motion in its classical sense ceases, yet quantum motion persists. A boundary where the ordinary and the extraordinary meet. Absolute zero represents an ideal, a limiting case that we can approach but never reach. And there's something profound in this unattainability. It suggests that perfection, in the sense of complete stillness or complete order, is not part of physical reality. The universe retains an irreducible restlessness, a quantum vitality that persists even at the lowest temperatures. This restlessness isn't a flaw. It's fundamental to how the universe works. Throughout this journey, we've seen how absolute zero serves as a reference point, a place where the mathematics simplifies and the underlying patterns become clear. Physicists use absolute zero to understand phase transitions, to calculate ground state energies, to predict behaviours at low but non-zero temperatures. The unattainability doesn't diminish its usefulness. If anything, it enhances it, providing a well-defined limit that theories can approach asymptotically. But beyond its scientific utility, absolute zero invites contemplation. What does it mean that the universe has limits? That there's a coldest temperature, a fastest speed, a smallest distance where physics makes sense? These limits define the structure of physical law. They tell us that the universe is not arbitrary but constrained, that certain combinations of properties are impossible, that reality has a shape and form determined by fundamental principles. And these principles, remarkably, are comprehensible to human minds. We can write equations describing matter at absolute zero. We can create experiments testing those equations. We can push the boundaries of the possible and confirm that our understanding, while incomplete, captures essential truths about nature. This is one of the great mysteries of science, that the universe is not only lawful but understandable, that human reason can penetrate its workings and predict its behaviour. The quantum phenomena at absolute zero also remind us that the universe is stranger than we might expect. At everyday temperatures, matter behaves predictably. Objects have definite positions and velocities. Cause and effect follow familiar patterns. But remove thermal energy, approach absolute zero, and these familiar behaviours dissolve. Matter becomes wave-like, probabilistic, non-local. Particles lose individual identity. States become superposed. The universe reveals an underlying strangeness that our everyday experience obscures. Some find this strangeness unsettling, a challenge to our intuitions about how reality should work. But there's beauty in it too. The universe at absolute zero is more subtle, more richly structured, more fundamentally quantum than it appears at higher temperatures. Learning to see this quantum nature, to understand how it emerges from the wave function and quantum statistics, enriches our conception of what matter is and can be. And perhaps there's a lesson here about understanding in general. Deep understanding often requires approaching limits, exploring boundaries, seeing what happens at the edges of normal experience. Whether in science, art, philosophy, or life, pushing to extremes reveals aspects of reality that are hidden in the middle ranges. Absolute zero is physics' extreme of cold, and by exploring it, we've learned truths about matter that we couldn't have discovered any other way. As we come to the end of this exploration, what should we take away? Perhaps simply this, that the universe, even at its coldest, is never truly still. That quantum mechanics ensures perpetual motion at the smallest scales. That matter at absolute zero exhibits behaviours, superfluidity, superconductivity, quantum coherence, that demonstrate how profoundly quantum the universe is, and that by pushing toward this limit, by creating the coldest places in the universe in our laboratories, we've opened windows into nature's fundamental workings. The still point, the place where all motion rests, doesn't truly exist in physical reality. But approaching it, getting ever closer to absolute zero while never quite reaching it, has been one of the most fruitful endeavours in all of science. It's taught us about matter's quantum nature. It's enabled technologies from MRI machines to quantum computers. It's revealed universal patterns in how particles behave collectively. And it's given us a cosmic perspective, connecting the coldest temperatures to the universe's origins and fate. The journey towards zero is, in a sense, a journey towards simplicity and clarity. Strip away thermal energy, remove disorder and randomness, and what remains is matter's essential quantum character. And that character, strange and beautiful and precisely mathematical, is part of what makes the universe comprehensible and wondrous. And so we've reached the end of our slow drift toward absolute zero. Thank you for staying with me through this entire journey, these 2.5 hours we've spent together, exploring the coldest temperatures imaginable and the quantum strangeness they reveal. It's a privilege to share these ideas with you, to contemplate together what matter becomes when we strip away heat and let quantum mechanics show itself fully. We've travelled from room temperature down to millikelvin, nanokelvin, picokelvin, approaching but never quite reaching absolute zero. Along the way, we've encountered superfluids that defy gravity, superconductors that conduct electricity forever, Bose-Einstein condensates where thousands of atoms merge into single quantum entities. We've seen light slowed and stopped, watched magnetic levitation through quantum coherence, contemplated the quantum vacuum's perpetual restlessness. We've connected the coldest temperatures in our laboratories to the cooling universe, to the formation of stars and planets, to the origins of everything we are. And through it all, one truth has emerged. Absolute zero is not emptiness, but essence. It's where matter reveals its quantum nature most clearly, where the strangeness hidden beneath everyday experience becomes visible and comprehensible. It's a limit we approach asymptotically, never reaching but always learning from, discovering patterns and principles that illuminate not just the coldest temperatures, but all of physics. If you've enjoyed this calm exploration of the quantum realm, a like and subscribe helps these documentaries reach others who are seeking the same peaceful way to learn and drift into sleep. Your support means more than you might imagine. And to those who've been here before, who return to these slow journeys through science and space, thank you. This small community of curious minds makes creating these videos worthwhile. Wherever you are in the world right now, I hope you're comfortable. I hope your breathing has slowed to a gentle rhythm. I hope your thoughts have quieted, that the day's worries have faded to background whispers. I hope your body feels heavy and warm, sinking into whatever surface supports you, released from the need to hold itself alert. Look up at the night sky. if you can see it from where you are, or imagine it if you cannot. All those stars, all that space between them, filled with cosmic microwave background radiation at 3 degrees above absolute zero. The universe itself is cold. Growing colder with each passing eon, approaching but never quite reaching that ultimate limit. And in that cosmic cold, quantum fluctuations persist, ensuring that the universe is never truly still, never truly empty, always alive with subtle quantum motion. Perhaps that's what we should take from this exploration. That rest isn't about absolute stillness, but about finding ground state, about settling into the lowest energy configuration while retaining the minimum quantum motion that makes existence possible. That perfection isn't about reaching absolute limits, but about approaching them gently, learning what they teach us without demanding they yield completely. In the laboratories scattered across Earth, scientists continue their slow approach towards zero, cooling atoms to temperatures colder than anywhere else in the universe, studying matter's quantum nature, building technologies that will shape our future. And in the cosmos, matter continues its slow dance between heat and cold, structure and entropy, complexity and simplicity. We exist in the middle, warm enough for complexity but cool enough for stability. Part of the universe's long cooling from Big Bang fire to eventual cosmic chill. Sleep well tonight, knowing you're part of this vast process, stardust temporarily organized into conscious form, able to contemplate absolute zero and understand, even partially, what it means. Dream, if you dream, of quantum coherence spreading across clouds of atoms, of superfluids flowing without resistance, of matter at its most fundamental, stripped of everything except quantum essence. Dream of the coldest possible cold and the beauty revealed there. Good night.